So I'm going to start with GPU solver additions. Now, I say GPU solver, but it's more than that. This is actually a rewrite of Fluent. So those of you who are Fluent users, some of you probably think, hey, it's probably about time that there has been that there is a bit of a rewrite. It's a pretty old code base in some areas. There's a lot of legacy stuff that's not necessarily required anymore, but it's hard to take it out. So what's happening is essentially Fluent is being rewritten. It's being rewritten in a hardware agnostic manner, so it runs on GPUs. So we're calling it the GPU solver. It will run on CPUs, and it's just a fresh version of Fluent, essentially. So what we've got up here on the screen at the moment is sort of the current timeline. Let me just get the pointer thing. This one. Cool. So yeah, this is a bit of a history of the GPU solver. It's quite new. Back in 2022, it was kind of like alpha, beta. It did very, very basic stuff. But it's now getting to the point where it's actually usable. Particularly 2024 R2, I've personally been using it for consulting jobs and getting really good results with it. And in fact, it's allowing me to solve things like proper jobs on my laptop instead of having to take up all of our more expensive HPC resources, so they can be left to other people without GPU solvers. So getting straight into it, some of the like UI UX kind of improvements, just like usability that's come in the latest release is we're getting more monitor support. So monitors are obviously quite important for anyone doing CFD. You can't really just rely on your residuals to tell you when a problem is converged. You like to instead look at a monitor of a quantity of interest. We're now essentially just supporting more and more of those. Probably the big outlier still is flux reports. So flow rate stuff, it's not in there just yet. Although we've got mass flow rate, so this is more like flow rate on say if you wanted to get like the flow rate of a species through a boundary. That's not quite in there yet, but it should be pretty soon. And another really big one here is expression support. Not just static expressions, also dynamic expressions. So hopefully if we have time, we'll have a look at some of those in a demo. And just a bit of a usability thing here as well. We've got sort of faster post-processing. So rather than have like the information on the GPU getting ported back to the CPU and then rendered again on the GPU, we now have like direct post-processing on the GPU solver. So it's much faster to display contours and all of that good stuff. Just some physics. We've got a couple of turbulence model enhancements this year. One of them for you aerospace folk. We've now got the transition model working. This is just the algebraic formulation, which is actually probably my go-to model these days anyway. It's very fast and very robust. So that's in there. It's in beta, but it works quite well. We've also got curvature corrections. So anyone doing in particular cyclones where you need to resolve that like central vortex, curvature correction is required pretty much for a 2-equation turbulence model. That's now in there in beta as well. This is something I've been waiting to come in. I thought this was probably one of the most obvious use cases for the GPU solver, which is acoustics, because the GPU solver is fantastic for solving like long transient simulations really, really quickly. And a really good use case for that is, of course, to resolve acoustic problems. So we've now got the Fawkes-William-Hawking model in beta. It can essentially, it runs the simulation on the GPU and it exports some data, which does run on the CPU. I think we're expecting to see it like fully GPU native in coming releases. And as you can see here, we're getting some pretty decent performance. You'll see this number show up on lots of different slides, and you'll see that some models scale really, really well. Others don't scale quite as well. So you'll see this number sort of go between 200 and like 1500 CPU cores equivalent, depending on exactly what's being solved. Going back to aerospace, we've now got the far field pressure boundary, which is a fantastic model for anything going up above, anything compressible really. And something that's new here, if you've been trying to use the GPU solver in the past for anything above Mach 1, we would have said maybe not just yet. We'd say that it was for mild compressibility, but we can now push up above Mach 1 I have it on good authority from some close contacts at Ansys that it's working well up to about Mach 3. Someone's even testing it at Mach 7 and having pretty good results. Obviously, it's going to be case specific. I can also say that there is a density-based solver in the works. Not sure when it's going to be in, but that's going to then have like the full hypersonic suite in there as well at some point.
Okay, yeah.
Onto turbo machinery, another really good use case, particularly like the transient stuff where we're doing interactions between rotating and stationary components. We can now do, so long as you've got matched interfaces, you can do like non-conformal sliding mesh type problems. So you can see here, result on CPU and a result on GPU, but probably what's still lacking are the sort of more advanced frame change models in there. So if you want to do like full wheel stuff, if you want to do multiple blade row type simulations, you are currently best off on the GPU solver using the full annulus. I've got a really cool example here. So here's one that was done. It's a full 2.5 stage compressor. So we've got 3 stators and 2 rotors there. And this plot here, it might actually be pretty hard to see because they like directly overlap, but you can see the CPU solver and the GPU solver got pretty much identical results. The speed up on this wasn't quite as big as some of the others that we've seen in the past. This is, I think, somewhere around 200 CPU cores per GPU for this one. Although keep in mind this is an L40, it's not an A100, so a slightly lower tier GPU there. And isotropic conduction is now in, so probably a pretty good use case of this. Anyone doing like electronics cooling, you want to have a printed circuit board with orthotropic conductivity, so maybe it's got good conduction across it but not through it. That's now available in the GPU solver. We're starting to see some combustion come in. So we have the eddy dissipation model. I think that was in a previous update, so if you saw my talk last year, I would have covered that. But we've now got the adiabatic FGM model in here as well. And you can see that it's got some really nice alignment with its CPU solver for non-premix, fully premix, and partially premix combustion here. And this is all kind of leading towards, again, sticking with the aerospace industry theme, being able to solve, combustors for aircraft. So we've now kind of got the external aerodynamics, we've got some of the turbo machinery, and we've got the combustion to sort of support that full range of simulations that's required. Of course, can't forget radiation for combustion problems. So we've got 2 radiation models in now, discrete ordinates and also surface to surface. So, anyone doing maybe like solar problems, you want to map a solar loading onto the top of a warehouse or building or something like that. Surface to surface radiation can be really good for that. DPM is now in beta as well. And we've got sort of one-way coupling for mass transfer in there. So you could have, some liquid fuel and it's able to evaporate and go into your gaseous phase as a species. That's now in there. I will say that of all of the features that are beta, this one is actually still quite beta. Probably would be waiting for 25.01 to play with this if you were curious. Sticking with the multi-phase theme, this is one that I actually ran as part of the testing for 2024 R2 that we did for Ansys, going back quite a few months now. But we now have VOF on GPU, and this is a demo that we're going to look at really, really soon. It's an alpha feature, but for this particular problem, it worked really well. I'm not suggesting that everyone go out here and try and use it straight away, but I want to give a bit of like a sneak peek into what's coming, because I know a lot of the users in this room are multi-phase people. And you're probably looking at all these GPU updates being like, cool, but I don't do external aerodynamics. When can I solve some real industrial problems? Well, it's coming. VOF is where it starts, of course, and we're going to expect to see, full Euler mixture model stuff coming in further releases. I don't have any timelines for that though yet. Sorry. I mentioned expressions briefly at the start. Just a little bit more context, I guess. So you can see that we've got the, your standard static expressions there, X, Y, Z coordinates, all of that. Some of the math functions in there as well. But something that's, I think, a bit more interesting that's sort of happened in this latest release is the dynamic stuff. So here you can see that the expression that's used for this little demo, which is another VOF case actually, is a function of time. So you can see the sinusoidal profile applied to this geometry down here to change the gravity vector. UDFs and customization. This is quite a change from the existing solver. I will say straight away that some C-based UDFs, so like existing UDFs for the regular CPU Fluent solver, are available, but the number of macros is severely limited. So if you've got a really complex C-based UDF, you probably won't be able to use it in the GPU solver. It is being replaced with a Python-based UDF system. Obviously much faster to develop your code in Python, probably a little bit more flexible as well, being able to use more third-party libraries and that kind of thing. So yeah, this is an area that's probably going to really change the face of code customization in Fluent to come. Moving on to some of the performance improvements. So scalability has been a big theme of particularly 2024 R2. So we've always had really good, I say always, for the last couple of years since the solvers existed, we've had really good performance on like a single GPU or 2, 4, 8 GPUs even, but it did start to taper off after that. So you can see here in this graph that 2024 R1 at the 24 GPU mark was really tapering off, and at 32 it's even gone backwards. But we're now starting to see that just like continual near linear increase in performance on the latest release. And to take things one step further, I really like this graph. I think it really does just hammer home how much faster this is. If we look at the baseline case here, our 1x for speed up, that's 512 core cluster, right? So this is not a small system. So these light gray data points here are all CPU solver. You can see our last point there is 12,000 cores. If we then look at what the GPUs are doing, you can see up running on 64 L40s is 77.5 times faster than 512 CPU cores. So we're talking about some seriously impressive pace here. They've also done some testing on newer hardware, so H series GPUs, which they're actually not that new. They've been out for a while, but they're like gold dust, so hard to get your hands on. For these kind of like standard single precision external error type problems, we can see up to about 1,500 CPU cores per H100 GPU, which is pretty crazy. I know we've been talking NVIDIA a lot. We do now have support for AMD GPUs. Currently, it's just on the Linux version, although I would expect in 25 R1 that this is going to be available on Windows as well. The AMD stuff currently just hasn't been as optimized as NVIDIA. So like an MI300X, which is like brand new, super high-end AMD GPU, is kind of on par with an A100 for a segregated solve, although it is a bit faster for a coupled solve. So it's probably not quite on par yet with like a H100 or H200, GH100 from NVIDIA, but we're expecting to see more performance improvements come to AMD in coming years as it's developed further. Just the last few things, just covering some numerics improvements on the GPU solver. So it's now got poor mesh numerics. You can see here in this sort of dummy case that they put together, we've got a solid conduction one down here. So you can see obviously terrible cell down here without poor mesh numerics. You get a super unphysical result. Now, poor mesh numerics can do a few different things. Like sometimes it'll essentially remove a cell, which is essentially just like a zero order interpolation. It'll just take the value of whatever's next to it. Sometimes it'll use like a first order or like a linear interpolation from the two cells either side. Not entirely sure exactly what the implementation of this is at this current moment in time, but you can see when it has been enabled, I'm guessing this is a zeroth order approach, that those unphysical values are gone, and we're now getting that really nice solid conduction through here. And likewise with a flow case over here as well. Obviously super unphysical velocities in here that have just been smoothed out nicely, and the convergence as a result looking much better too. And a few other little things. Probably the main one I just wanted to point out is the top one. anyone that's used Fluent as a like steady state solver just for your basic kind of external or internal error, you'd be very used to, over the last few years anyway, the default formulation being pseudo transient with like the automatic time step calculation that you could maybe scale it up or down depending on how you see your convergence going. That wasn't in the GPU solver until now. So if you were to fire up the GPU solver as of 2024 R2 and run a pretty straightforward steady state case, you'll find that the defaults are now pretty much exactly in line with the CPU solver. It's going to feel really, really familiar to you. A few other things there. In the interest of time, we won't cover all of it. Just my last little topic on GPU solver is this remapping feature. Now, a lot of the slides here from Ansys are going to be more talking about these huge multi-GPU configurations that maybe not so relevant. In Australia, a lot of us are probably more like SMEs, and we might have one or two big GPUs to play with. So I just want to stress that this is not just for those huge cases. So I'm just going to go on to the next slide that kind of shows what this does. But essentially, I'm going to talk from a single GPU perspective, but the same applies to what you can see on the graph there. If you have like an A100 or something and you're trying to load a mesh that's 30 million cells, you don't really want to just use one CPU core to support that, because it's going to take a while, right? It's like you just got one core processing this huge mesh file. It takes quite a few minutes to do all of your I/O. So you want to be able to use, I don't know, maybe 16 cores or something like that to handle your I/O. What happens though when you do that is you end up with like 16 different threads handling the CPU to GPU communication. I won't go into detail, but essentially that results in overheads that slows the GPU solver down. So what this CPU to GPU remapping does is kind of give you the best of both worlds. You can use your 16 cores and get that improvement in I/O, but you don't end up with the solver overheads of having those additional processors sitting there on the GPU. So in this example, we've got 8 cores here. So yeah, we've got 8 GPUs with 8 threads. I'll say for every GPU, you need at least one thread, one CPU thread to handle it. So this is like our default case. But you can see here, this yellow part is the I/O, right? That's the case read. And we're only doing 1,000 iterations. So this is like the total time's not huge. But you can see here, if we wanted to use more cores and bring that yellow down, we had this huge overhead in solver performance. So now with this GPU remapping, we can see that we kind of get the best of both worlds. We've got the fast solve time and the fast I/O. It's not perfect, but it's very close to being a mix of the best of both. Alrighty, I'll step out of this and go into our first demo. I think we're doing pretty well on time. 20 minutes in. Cool. Sure, I open the correct one. All right, so this demo is definitely more on the sneak peek side of things. So I want to show you just real quickly the VOF solver running on GPU on my laptop right now live. I'll show you the setup very quickly and I'll hit run and we'll come back to it in a few minutes and see how far it made it. But just for context, this is a 4 million cell mesh, so it's not a small problem. It's not a huge problem, but it's not small. It's a decent size to run on a laptop. And our mesh in here is quite fine in our region of interest. So you see, like, this is the front. It's a 3D problem, but just on the symmetry plane anyway. This is the front of a hull, and we've got our water level is where all of these sort of inflated cells are. And then we're going to have quite a bit of churning and some bow waves sort of forming up the front here. So there's quite a fine mesh up there, and likewise at the back, we've got quite a fine mesh back there as well. Just to sort of show you what the setup looks like. When we expand models here, there's not all that much available to us, but because I have enabled the alpha feature, you'll see that we've got VOF sitting over here. A lot of it's grayed out because, again, it's alpha. It's pretty much just like the default configuration. But I've got an air phase and a water phase, of course. I don't have access to things like open channel flow. So I can't just use the like built-in shortcuts that open channel flow gives you for the boundary conditions. So what I'm doing is making use of some dynamic expressions. So I'm setting my pressure profile here where I've kind of got like my water height is at 1.4 meters. So anything below 1.4 meters is getting hydrostatic pressure from the water, and anything above is just set to atmospheric. So that's what that one's doing. And much more boring, this is just saying water below 1.4 and air above 1.4. So if we go into our boundary conditions real quickly, we can see that, I'll just go to phase water. You can see that we've been able to use that expression in here. So this is a new feature in the GPU solver, being able to use expressions for these kind of fields. And then likewise, I won't show it, but on the outlet boundary, I've applied that pressure profile. Likewise, when we initialize it, I've been able to patch those two profiles into the domain as well, so that that's where our starting point is. I won't redo it now just because it will take a little bit of time. But I will quickly show you what our two animations are that we're going to have running as this solves. So first one is going to be, oops, I clicked the wrong button. I meant to show preview. Wait for that to load. Yeah, now first one's just this like side view. We'll see the water level there. Pretty straightforwards. Our other one's maybe a little bit more interesting, like a 3D view here of the free surface. So we'll see the free surface like start to ripple as we get some waves forming. Yeah, so that's what we're going to be monitoring during the simulation. And just here as I go to hit run, one last thing I'm going to point out is look at the time step I'm able to get away with straight from the start, right? I'm not ramping this up gently. I'm not going down to 10 to the minus 4 or something to help it get started. I'm just going straight out of the gate at 0.01 of a second, which is pretty decent for VOF. And we're just going to hit run, and hopefully it doesn't crash on me. The live demo, so probably going to crash. Cool. We'll just let that do its thing. I'll go back to the slides, and hopefully it's been solving. I might just give it a chance just to do the first time step here. It does just take a second to get started because currently, as you like read the case into the GPU solver, it's kind of still sitting in your system memory. When you hit solve first time, it will push everything across onto the GPU and then start solving it. So this first time step after you hit calculate just takes a second, and it'll tell you that you've got some features exposed that aren't yet released. So I've got two alpha features, one of them obviously VOF, and the other one is bounded second order in time. And there we go. Okay, so it started. One thing I'm just going to point out here as well is it looks like it's just run some iterations incredibly quickly and then halted. That's not actually the case. What you're just seeing here is like asynchronous reporting. So the GPU solver doesn't like reporting out residuals at the end of every single iteration to the process, to the main process here, because that slows it down, right? What it prefers to do is do its calculations, and then at the end of a time step, send that information across to the Cortex process, which is what we're seeing here. So that's why it kind of looks like it just goes like smashes through 20 iterations and then pauses, and then smashes through 20 iterations. It's just asynchronous reporting. So don't worry about that too much. Anyway, it's underway. We'll come back to that in a few minutes and see how we've gone.